The motivation is now to suppress the carrier transmission so that we save power and we can put more power into the sidebands or in the RF band so that the signal to noise ratio at the receiver side is better for reception. And we have now an RF band here where only the information is present and there is no carrier. Now we only have the two side bands and all power is in these two side bands which carry the information, and we don't waste power on the carrier. So this is called the double sideband modulation with a suppressed carrier. It's a certain type of the amplitude modulation, and now you may notice that actually we can save more power because the information is present twice. So in the lower sideband and then in the upper sideband. Yeah, so both sidebands carry the same information. This comes from the baseband here. Remember that the baseband has to be symmetric if it is a real valued signal. So on the positive side and on the negative side there is the same information but just mirrored. So actually you can save more power by just transmitting one band, for example the upper sideband, and suppressing the other sideband. And this modulation type is called single sideband amplitude modulation. But we will not go into in detail into this. This is actually used to transmit voice signals, so analog information, but we won't focus on single sideband transmission here for digital communication systems. So now you have an idea what it looks like in the frequency domain, and now let's switch to the time domain. Here again it's a plot of our carrier in blue and the information in red, and this was our mathematical description of the double sideband modulation with a transmitted carrier. So here's the carrier, here's the signal modulation index, and here's the multiplication which realizes the amplitude modulation, and we have +1 here. So the +1 actually did in the time domain took our information and then shifted it up. So the information here in red was shifted up here, and then it is multiplied with the carrier, and this +1 has had the effect that the carrier is still present. Yeah, so the +1 is then multiplied with the carrier, and then the carrier is present in the signal. And if you have a look at the mathematical description of the double sideband with suppressed carrier modulation, this +1 is missing. So the information is directly multiplied with the carrier. And this is the result. The information is not directly located in the envelope, which would look like this here. This is our envelope now of the modulated signal. This is not the case. The information is now present on this, let's call it extended envelope. It's not the correct term, but you know what I mean. And yeah, you might argue that the carrier is still present here, but it is somehow changed. So you cannot directly see the carrier here, although the frequency of the underlying oscillating signal here in red is the same as the carrier frequency, but here at this point you see a phase shift. So the carrier is obviously modified a bit more than in the previous double sideband modulation. But what remains is that the carrier and the information signals are multiplied, which leads to a convolution. This remains the same, and if we go back to the frequency domain representation, the signal here still looks the same, with the difference that the carrier is missing. And now let's have a short outlook onto the technical realization of our double sideband with suppressed carrier amplitude modulation. The responsible thing for the modulation is the multiplication, and here you see a block diagram, and this multiplication is represented by this symbol. So it has an X which represents the multiplication, and the inputs to the multiplication are the carrier signal and the information signal, and the output is the double sideband amplitude modulated signal. And we will see this this block symbol very often in the next videos, and this block symbol represents our mixer. So this multiplication here will be the basis for mixing, which we consider in future videos. But before we will discuss mixing and the technical realization of modulation, we will consider the other modulation family, the phase modulation.